So this work is about resources in programming languages, and in particular, how can we use them as safely as possible? And we want to guarantee the safety from a statistical perspective. So we are going to go after nice type systems, nice semantics that we guarantee. So maybe I'm sorry for the crackling. So a running example that we will be considering is a snippet from a code that you might find in a program that's running on some assembly line. So what we're going to do is we take some items like elements of a car, we are going to paint them, and then we're going to assemble them. What we are not going to do here is talk about topics like linear types, session types, for example, some finalization guarantees. We're not going to talk about how such resources are used. What we're going to talk about is when these resources are used. Because if you look at the snippet, then the guarantee or the correctness of it kind of depends on, for example, that enough time has to pass between the paint operation and the assembly operation. So the idea throughout this talk is that even though after doing the let and a bit of pattern matching, we have these items at hand, we might not be allowed to use them for either a certain amount of time or a certain amount of kind of state changes or events happening. So, for example, to guarantee the correctness of this kind of code, a scheduler might dynamically block us here until enough time passes. A compiler might insert enough time here during compilation, or delay here to ensure enough time passage. Or the same robot arm could do some other useful work at the same time. So we could just turn 90 degrees or 180 degrees to another line and do some work there, and then come back once enough time has passed so that we are actually legally allowed to assemble the bits. And the question is, how do you reason about any of these things kind of being correct, and how do you do it in a single framework? And that's what the rest of the talk is going to be about. So what we're going to do is we're going to extend a very basic effectful lambda calculus based on Paul Levy's fine-grained call-by-value lambda calculus with a bit of model types that will be created by time, and we'll see how this actually guarantees the kinds of properties that we're interested in. So first of all, we could also look at just a naive solution attempt. So if you just stay in fine-grained call-by-value or Camel or Haskell, whatever your favorite effectful language is, maybe we can just get by the paint returning us the time that needs to pass, then we do a delay, and then we'll assemble. One can ask, are we done? Of course, the answer is no, because I mean, nothing guarantees that the delay happens here and not after assemble, or it happens at all, and so on. So we would like to have a type system that guarantees that there will be some property attached to these resources after they come out of the painting operation, that we are really not allowed to use them before something happens. So that something might be a delay, so that something might be other operations that take enough time. So the way that we do it is we extend, as I said, a basic effectful lambda calculus with modal types, and the major extension is adding to the value types a box type. And there are two ways how you can read it, depending on which direction you're looking at it. So box tau of x essentially denotes the idea that a resource of type x will become available at most tau time units in the future. So, or if you look at it sort of slightly different angle, then at least tau time units have to pass before we can access the value x. So the idea is that even though we have something of type x at hand, we will not be allowed to use it before enough time passes. And in this talk, for simplicity, I'm only going to grade these modalities by times. So we're only going to look at time specifications, but there's nothing stopping you to pick other suitably ordered monoids here. So this could also be like state changes or sequences of events or traces of events or operations coming from your program. And then this allows us to talk about resource values. So these these would be the values that were that we got as the result of the left binding before, and now we can attach or give them the modal types. So the idea is that after painting, you get back a car part, but it will be boxed under in this modal type, which will guarantee that enough time. So this particular tau here has to pass before you can actually use car part. The way that it's presented is through a fit style presentation. So some of you might know it, some of you might not know it. I'm not going to go into too many details of the general story about fit style modal type systems. We're going to only look at what applies here in our situation. And the key aspect is that when we look at what happens with the context in our typing judgments, then we have the usual empty context, context extension with variable, but now we also have an additional modality that you can apply to a context. And the way that you should understand it is we read the context from left to right, and then this modality here captures the passage of time. So when you look at this context, then any variables in gamma were bound or brought into scope tau time units in the past. So, for example, when you look at the introduction form of these modal types, then in order to box a value of type X and then give it this resource type, we have to be able to type this value hypothetically in a tau time units in the future. So if you kind of, at this point in the conclusion, we think of the end of right-hand end of gamma as being time moment now, then we want to guarantee that V will be usable sufficient in the future. So we need to be able to type V in that given future, these tau time units in the future. And then there is, of course, an elimination rule. So unboxing, mostly looking very unsurprising. You get the value of box type, you have a continuation where you can use the unboxed value, and then you do whatever you do, and then finally return something of type Y. The tau primes after the bang are just coming from the effect system. So this is, after the bang, this is like a graded monad-spaced effect system. You just count the time. So unbox, in this sense, is going to be a no-op. It's just an administrative step. The whole unboxing takes the same amount of time as the continuation. But where the interesting bit arises is when you look at the V, the value that we're trying to unbox, it wouldn't be safe to just type V in the current gamma. Because what we want to say is we can unbox this value, but only if it was brought into scope or only if it became available enough time in the past, so that our now that we're trying to unbox it at is enough in the future compared to where it came into scope. So that's why we have wrapped the gamma in this operation. And what this operation does, it just deducts tau time units worth of variables and modalities of the context. So if you look at what it does on a concrete example, then if we have this context, and as I said, you should read it from left to right. So X was brought into scope, then 4 time units passed, then Y was brought into scope, another time unit passed, and then Z was brought into scope. So now when we essentially do a minus operation on this context with the with time 3, then we remove this Z, we remove this 1, then 3 becomes 2, we remove this Y, and finally we remove the remaining 2 time units from 4, we arrive at that. So the idea is that, yes, in order to be able to unbox something now, it had to be brought into scope or constructed enough time in the past, so that it's safe to do it now. And then for the more semanticists in the audience, it turns out that this operation actually turns out to be now a parametric right adjoint to the context modality. This is if you care about the generators of the fit style model type systems. Yeah.
Time of gamma.
Oh yes. So time of gamma is, let's say, it's in a way it's a safeguard. So this makes sure that time of gamma is just counting, adding together all the times in the context. So then this side condition here is basically saying that we want to guarantee that we don't jump past the Big Bang. So we don't go too much into the past. And that's where this parametric right adjoint situation is coming from, because it's part of basically having the adjunction. That this you apply this operation only to contexts that have enough time in them. Computationally, nothing surprising. You have a beta rule, which just says that if you unbox a box, you substitute the value into continuation. You have an eta rule, which is also expected, so nothing surprising. The system also very naturally has the usual structure rules, so weakening, contraction, variable exchange. You also get a bunch of very natural temporal rules. So passing zero amount of time is the same as doing nothing. You can passing a composite amount of time is the same as passing single steps or smaller steps of time. If I was able to prove something with a variable available now, then it's also possible that I can prove that variable becoming available in the future. So in this particular work, we are only looking at non-expiring resources. So there's a monotonicity property that once something becomes available, it will remain available in the future. Expiring resources, one of the ongoing future directions. And then all these admissibility rules, you can very nicely prove from the fact that you can construct a very nicely computing category of renamings. So those who have done formalized renamings in Agda, you might sort of see some similarities in this type with your usual simple type lambda calculus side of things, that if I take a variable in gamma, I will return a variable in gamma prime, the same type. Now, the only difference is that here, this subscript tau is counting how much time has passed since that variable entered the context. So the time right of the variable and the variable that you are returning in gamma prime has to have at least that much time on the left of it, or to the right of it. This guarantees that when you're doing renamings, you can't suddenly decrease the time. So the time can only grow in one direction. Yes. So I've told you about how to box resources up, how to unbox them. And we saw that it's, in order to unbox a resource, it's very important that enough time has passed. Then the question is, how does the time pass? How do you actually make time pass in your computation? And that's where computational effects and algebraic effects in particular come into the picture. So in addition to boxing, unboxing, and let bindings and returns, we also assume a set of graded operation signatures. So here's just an example. So kind of coming back to the original example, is a paint operation. So it takes a collection of parts, it returns some collection of parts, each wrapped in a temporal modality, and itself takes tau paint time units to compute. So this is the red part is how much time the paint takes to compute. And then when you look at it, how it appears in the language and in the type system, then it's almost like a usual graded algebraic effect operation. So we have the continuation, it takes tau time units. When we apply paint, then the whole computation takes the time of the continuation plus the time of the operation. The main difference here is that whilst with usual algebraic effects, you would just extend your context gamma with a y. That's the result of the operation. But here we are also in the context tracking how much time has passed. So the continuation of the operation will know that at least that operation's worth of extra time has passed before you start accessing the return value, which means that in M, we can potentially unbox new temporal resources because more time has passed compared to the beginning of the program, so beginning of the compared to the gamma that we typed the whole program in. And the same kind of thing also appears in sequential composition. So this is maybe even simpler to read than the previous bullet point. So we have a computation that takes tau time units. We have another computation that takes tau prime time units. When we sequence them together, the whole overall computation takes tau plus tau prime time units. But now the difference with their usual let binding is that the second computation can safely assume that tau time units have passed, which means that now in the second computation, we could, again, unbox some extra things because more time has passed. I also have effect enders. The story is the usual as with effect enders. The main difference is that when you look at the operation clauses, so this is this last premise line here, then the continuations will also be boxed. The continuations are guarded that you can only call the continuation if enough time has passed, and the time is this operation's runtime. So it kind of gives you a form of a linear behavior, because you can really only call this continuation after, at the end of running your computation, and you can really only do it once. Because if you do it more than once, then you wouldn't be able to match the effect annotation for the whole computation. And also for the overall continuation, so the return clause, again, the return clause can assume that enough time or the time has passed. So the same amount of time as the time that of the computation that you're trying to handle with. And now if we go back to the kind of the running example, then if you write it in this formalism, then the type-safe version looks like this. So we do our painting, then we do a delay, but now as the delay is with the right amount of time, so the time that was required by these resources, we can unbox the resources and then finally safely assemble it. And the reason why we can do it safely is that if you look at the context at this line, then we have the original gamma, the resources that we got from here, but then also the delay operation adds an additional time modality to the context. So at this point, it's now safe to unbox this value because enough time has passed. So compared to the naive solution, the only real difference is these kind of auxiliary explicit unbox operations that you have to do. Otherwise, it looks like what you would have done in a very naive approach, but now it's type safe. So it's the case that you can't suddenly or accidentally move this delay after the assemble or leave out this delay altogether, because otherwise the unboxing wouldn't work anymore. And of course, as I said in the beginning, one of the desires was that it shouldn't be only restricted to adding delays and then just blocking execution. But if you want to be more efficient, you might want to do other useful work whilst waiting for something to dry before you assemble it. And this is, of course, possible because instead of the delaying, you could run a sequence of other useful operations. So the ARM could do something other useful before getting back to these resources. And then in the last couple of minutes, I'll walk you very briefly through the denotational semantics that's used to justify that the language design is actually natural and actually correct. So the equational theory that you saw glimpses of before is actually corresponding to something mathematically correct and natural. So the idea is that we will work in some underlying category that has enough structure, so products, exponentials, and so on. But mostly we will concentrate on a very concrete example, which is a pre-shift category. So we're going to look at functors from natural numbers with the usual order into sets. So the idea is that you can now think of every type interpreting a time-varying set. So every time moment, the type will have some values in it. And in this setting, as the time goes on, more values might become available in a given set. And this is also very similar to what you would see in a Kripke's possible word semantics of modal logic. The only difference is that there you would take discrete natural numbers or discrete words for your indexing. Here we take them with the order, which guarantees us this kind of monotonicity then. So for the modality and types, we pick a strong monadic functor, which just means that we have natural transformations like this. And in the pre-shift example, we define it concretely like this. So the idea is that the boxed values of type A at a particular time moment t are the values of A at tau time units future compared to t. We have a similar strong monoidal functor to also model the context modality, or the modality of the context, where now applying this modality to an A at t is going to give us the A values in the past. So this corresponds to what we were also doing on the context that we wanted to move to the past. We have a family of junctions. So this is mainly to relate these two modalities. And if you look at what the units and co-units are doing, it's really about being able to push resources forward in time. So if you have a type, a resource A available now, then tau time units in the future, I will know that tau time units in the past, I had an A available, and vice versa. If tau time units in the past, I knew that tau time units in the future I have available, A available, I will also have it now. For modeling the effects, we have a gradient monad, and this is one point to pay attention to, that the gradient monad structure is your standard one. There is no modalities creeping in here. The only place where the interaction with the modality happens is in the strength. So usually you wouldn't have this modality at all here for a strength, and you just say that, well, the strength is pushing these A values under the T and you return pairs. But now with the modality, you are additionally actually asking or saying that, well, this A has to be available in the future to be able to move it under a T that takes tau time units to compute. And this strength, while it looks a bit weird, is actually quite natural because you can relate it to a modal variant of enrichment. And then we have algebraic operations and handling. And for the concrete model in the concrete pre-shift example, you can just build it inductively. So you have return cases, you have operations, you have delays. The only thing is that when you formalize it, for example, in Agda, then induction recursion is needed because you actually want to refer to the exponentials in the pre-shift category. And you can't kind of just fake it on the underlying functions. And time to wrap up. So it was a fairly short or brief overview of what's happening in this work. If you want to know more, then do come and chat. And one thing that I didn't really have time to discuss in this talk is sort of a very recent and ongoing work with Kasper, where we're also looking at an operational semantics in this language. And in particular, we didn't want to just turn our equational theory into directed rewrite rules, but we wanted something that takes time, say, seriously. And actually what we ended up with is a stateful operational semantics where you think of box as an allocation-like operation. So boxing a value up is like allocating a reference, and unboxing is like a lookup. And then you run into non-trivial questions about, okay, how do you actually describe that enough time passes in the equations? So, and then we end up with the usual type safety results, but also we have equational soundness compared to a reasonable equational theory for these operators, which is a variant of the local state theory that various people like Sam Staten and Paul Andremelia have investigated. And that's it from me now. So thank you for listening.
So thank you. We have time for a few questions.
Thank you for your talk. So here you use a time-graded modality to control the time for operations. So I wonder whether it is possible to replace it with some other modalities. For example, you can specify how many times the handlers can use its continuation or something similar.
So if you are going in that direction, then you might want to look more towards co-effects and the style of work there, because co-effects would actually give you ways how to count how many times a particular variable is used, and that particular variable could be continuation. Example. I think it might, yeah, I'm not sure whether it would fit, that particular example would fit into this line of work.
Yes, another question.
So first of all, I like the calculus a lot. Can you go to the context restriction operation on the slides?
Can I go back to it?
Yeah. And in the meantime, have you considered using something other than natural numbers to indicate the passing of time?
Then I would need to jump on the last slide.
I'm sorry about that.
Okay. This one?
Oh, the reason I'm asking is, so this one removes resources, but really what it does, it shifts the context and time, right?
Yes, so it moves you back.
You work with negative numbers to make those unavailable. So you don't have to delete the actual entries from the context.
Maybe, but I don't know. Yeah, I don't. I haven't thought about it because I mean, negative numbers and digits are awkward to work with.
You don't tell time. Time tells you.
But just to jump back and regarding your last or your actually first question, maybe. Was it? No. Yeah. So one thing that is in the works and could be interesting is yes that you consider different monoids for grading, and not just that like we replace the natural numbers with some other monoid, but you also replace the monoid that you grade your effects with some monoid, and you replace the monoid that you grade your modalities with another monoid. So one example could be that you create your computations with traces, so you actually store more information. So you have actually store your sequence of, say, input-output operations. But your modalities could, for example, still be graded by time, or maybe you're just counting that a particular sequence of operations happen, not all of them.
Okay, we have time for one more question.
So your operations, when you showed handlers, seem to be kind of standard. They just have normal types. Would it make sense to somehow incorporate times in your operations? So you can say, oh, here's an operation that I know is going to take 5 seconds or something.
I mean, that's already part of the usual grading, right?
Oh, so you can express that already.
Where are operations? So this is just part of the usual effect grading. It's for every operation here, you say how much time it takes. So that's
the paint there is an operation in the sense of like an algebraic operation.
Yeah. Yes.
Right. Good.
Okay. Yes. So graded algebraic effects, graded algebraic operation signatures. The only difference here is that when you look at the continuation, then the modality pops up compared to a usual representation of algebraic effects where there are no modalities, and you would just be manipulating the effect annotations on the right-hand side of the band.